Oh, I just accidentally opened a program. Give me a sec to close it. Okay, so the plan for today is just to continue on with Chapter 7, confidence intervals. Last time we developed from first principles the confidence interval for mu when the standard deviation was known. And we talked about how that related to the confidence interval for P, population proportion. And today we're going to look at maybe a scenario that's a little more reasonable. When would we not know the population mean, but know the population standard deviation? That seems like that wouldn't be a very typical case. So today we're going to relax that assumption and ask, what about a confidence interval for the mean when the standard deviation is unknown? And then we'll also look at confidence interval for variance and standard deviation. And the quote of the day today is from a movie, probably from like the early 2000s or so, called The Truman Show with Jim Carrey, where I don't think any of this is a spoiler. It's a really good movie if you want to watch it. But basically, he's like a character in a TV show, but he doesn't realize that he's in a TV show. His entire life has been in this like enormous set, this whole town that they built specifically for him with all these cameras and everything to have this TV show, The Truman Show, where it's just like kind of like spying on his whole life as he grows up. And all the people that he knows are actors and all kinds of really interesting, um, ethics questions and so on that come up in this movie. But the quote that I like best from that movie is from this guy, Christoph, who's like the mastermind behind this whole show. Where he says, we accept the reality of the world with which we're presented. It's as simple as that. And, I think maybe this strikes me because I see today or for the last several years, a lot of people have been asking kind of what's the value of education? Why should I go to college? What's the value of a degree? And there are tangible answers to that, definitely, in terms of return on investment and the type of job you can get, the purpose that you might find in a job if you really really want to be a nurse, like getting that RN is very important, things like that. But I think there are also intangible things that as we grow up, any of us, we have naturally a world that we're presented. We have our family, our folks, our neighborhood, and so on, that presents a certain point of view of the world to us. Our parents work in certain fields, they're good at certain things and not great at other things and don't know anything about yet other things still. And that tends to kind of be passed down to us. And I think part of the role of education, a very large part of the role of education, is to present different realities, to have it. I think that's what's meant by a well-rounded education, or the liberal arts core, or general education, or the humanities, or all of those kind of general ideas, presenting different realities of the world so that everybody kind of moves out of their degree, whether it's an associate's, a bachelor's, whatever degree it is, with kind of at least some minimal footing in a lot of these different areas, a lot of these different possible realities. And I think that has a lot of benefits, not the least of which is we can maybe understand other people's perspectives and points of view better when we understand a little bit about what their reality might have been like and how it was different than ours. So I think that's just a really nice quote. A lot of movies and TV shows and so on, if you really pay attention and really listen to what's going on and the character development and so on, there's actually a lot of good ideas. You can kind of watch a lot of these things just as kind of surface level entertainment, or a lot of them have something deeper to them. Okay, so recall from last time, we developed a confidence interval for the mean. What was with that? When the standard deviation is known. my pen switched to a selecting cursor for some reason. Confidence interval for the mean when the standard deviation is known. And we said our goal was, well, we have an estimator. X bar is an estimator of mu, and it's a good estimator. We discussed what that means, but in particular, it means it's unbiased. But it's a point estimate of mu. So my best guess at mu is X bar, or maybe X bar observed, we started calling it. But I don't really have any idea of how good that estimate is. Am I saying that I think mu is about this number X bar observed plus or minus a really tiny bit, or plus or minus a huge bit? Do I think this is a really precise or accurate estimate of mu, or do I think there's still a lot of variability in this estimate? So we said we would like to develop an interval estimate. And we have to be a little bit careful with the technical nuances here, but we want to construct an interval like lower bound to upper bound such that I can say that I'm, for instance, maybe 95% confident that this interval covers the true mean mu. And then the question is, how do I find such a lower and upper bound? Well, I set a confidence level. I say, how confident do I want to be? If I want to be more confident, I have to have a wider interval, so I cover a wider swath of the real line, where, you know, you could think of mu as kind of like hiding somewhere along the real line, and the wider the swath I cover, the more certain I am that I have found a mu. So I need to know the confidence level, but I also realized that I could kind of shift my confidence interval left or right and get different confidence intervals. So I had one other criterion that I imposed, and that's symmetry about the point estimate, about X bar observed. In other words, I want to construct a lower and an upper bound that are centered at X bar observed and plus or minus a margin of error. And then the question is, how do I find that margin of error? Well, over here, we worked out that that margin of error has to be a z-score, a z-index, particularly the z-index with area alpha over 2 to the right. And what is alpha? Alpha is 1 minus our confidence level. So for instance, with a 95% confidence interval, alpha will be 5%. Alpha over 2 will be 2.5%. So we're looking for the z-index with 2.5% area to the right. That's what this bit gives us. And then times sigma x over root n, what we call sometimes our standard error, or it's the standard deviation of the random variable x bar coming right out of that central limit theorem. So our interval is centered at our point estimate at our best guess from mu. That's pretty sensible. It's an unbiased estimate. And then we go a margin of error to the left and a margin of error to the right to get our lower and upper bounds for the interval estimate. And we saw essentially exactly the same thing for P. The confidence interval for P, we have the point estimate, P hat observed. That's our best guess for P, and it is an unbiased estimator, plus or minus a margin of error that looks like a z-score, a z number, times, well, this might look at the surface level a lot different, but remember that for a Bernoulli trial, a binomial with an n of 1, the standard deviation is just root pq, or here we'd say root p hat observed, 1 minus p hat observed. So this is really just sigma over root n. And then when I have square root of stuff over square root of stuff, I can kind of like factor out the square root in a sense, use kind of a reverse distributive property kind of idea, and just wrap that all under a single square root. So it looks a bit different than up here, but it's really the same thing that's going on in the previous example, just with a slightly different surface level look to it. And we saw how things like looking at the number of ones that come up on a die roll, even if it's a little bit off of what we might expect from a perfectly fair die, we can develop confidence interval, and we can even actually go a little further and make even some other inferences, kind of starting to touch on the ideas in chapter 8. And that's about where we left off last time. Let me just clean up my formulas here. So that's where we left off last time. So what I would like to do now is I would like to relax this sigma being known assumption and develop a confidence interval from U when sigma is unknown. Oh, and kind of as an aside, our book starts with the confidence interval for P and then talks about confidence interval for mu in these two cases. Personally, I don't like that. I like starting with this because this is where our central limit theorem really comes from. We can then use that to generate both the confidence interval for P and to kind of relax that assumption and talk about this confidence interval. So, I mean, I'm covering them in a slightly different order than the book covers them in. If I didn't note that last time, just know that we're just kind of flip-flopping two of the sections in the book. Okay, so what's our goal here? Suppose we want to construct a confidence interval for mu when sigma is unknown. In other words, when it has to be estimated by S. So if we make our list of knowns and unknowns from our sample, if I can select it here, there we go. From our sample, we know, and the sample size, we know X bar observed, that's just the mean from that particular sample, that particular data set. We also know S, or S squared, the sample standard deviation sample variance. And then, of course, we know alpha, or our confidence level, that has to be given to us as well. And our unknowns are now mu as well as sigma. So up here, this margin of error had to account for the fact that I don't know mu, and I'm simply estimating it by X bar observed. This estimate of X bar observed, for some samples, it might be quite good, but for some other samples, it might be kind of far away from mu. That's what this accounts for. It accounts for the sampling error in estimating mu by X bar observed. That's really all that chapter 7 and 8 is about, is it's about how to account for sampling error. And that's kind of what we're doing here. This margin of error accounts for the sampling error and making this one estimate, estimating mu by X bar observed. But here we actually have two things we're estimating. We have to account for these two estimates. We're estimating mu by X bar observed, but we're also estimating sigma by S, or sigma squared by S squared. Well, there's more uncertainty here naturally, because we're estimating two things instead of estimating one thing and having the other be known for certain. And with more uncertainty, our margin of error should be larger. We should have to cut a larger swath out of the real line. We should have a wider confidence interval to maintain the same degree of confidence because of the increased uncertainty in doing two approximations, two estimations, instead of just one. Well, we know that in the example above, sorry, a fire engine or something is going by. Oh, ambulance, there we go. Okay. I don't know if you could hear that or not, but figured I'd just let them go by. So up above, when sigma was known, the central limit theorem says, well, one way of writing it is that, let me zoom this in just a little so you can see it a little better. One way of writing what we know is that Z equals X bar minus mu X bar over sigma over root n is standard normal. Why is that? Well, that's because our central limit theorem said that the random variable X bar is general normal with mean mu X bar and standard deviation sigma X bar is sigma over root n. Or I want my X bar to be on the other side. Not that it makes a difference mathematically, but was a little wonky the way that I wrote it. So here I have, if I standardize this, if I move from a general normal into a standard normal, using my z-score, I have the random variable minus its mean over its standard deviation. So now I might ask, okay, well, I don't know sigma now, but can I use the same idea here, the same x bar minus the mean over standard deviation over root n, but just pop in an s instead of a sigma? Can I do that? Or if I do that, does this still follow a normal distribution or a standard normal distribution? And the answer is, well, yeah, I can do that. And some very smart folks have come up with ideas about what distribution that follows, but it's not the standard normal distribution anymore. It's this other distribution called the t distribution or the student's t distribution. So a little bit of history. The history of this is kind of interesting. Trying to get my question mark away from here so that we can see it a little better. So the history of where this idea comes from and how it was developed and where this distribution and so on comes from dates back, I think, roughly 100 years ago to the Guinness Brewery in Ireland. And there was this guy who we now know his last name was Gossett. I mean, people know who he was. I don't remember his first name or know much else about him, but people know who he is now. And he was a brewmaster, whatever they're called, the guy in the brewery whose job it is to kind of make sure that the beer that comes out of the brewery all tastes the same, right? So obviously this is a pretty complicated process when you start thinking about it and you realize that the inputs into the beer are all things that are grown out in nature, the hops or barley or whatever. I'm not a beer drinker, so I don't know all of the details, but all of these things are things that are grown in nature. What if one season has more rain than usual, or it's drier or hotter, or the nutrients in this field are a little different, or right? How do you have this kind of quality control when you're combining together a bunch of natural ingredients? And that was basically his job. That was a component of his job, was to figure out how to do this, how to get a consistent output product when your input products can be somewhat inconsistent. So he was interested in statistics. At this point, statistics, as we're talking about it now, these inferential statistics like confidence intervals and so on, is a relatively new field, maybe 100 or 120-ish years old, something like that. So, I mean, this was around the time that this was maybe something like cutting edge research. Maybe not quite cutting edge in the field of statistics, but moving these ideas into kind of daily life in the scientific fields, I think probably would be described as cutting edge at that point. So he was investigating the ideas, particularly dealing with small samples, right? I mean, if we think about what's the difference between knowing sigma and not knowing sigma if I have a sample of size 100,000. Well, with a huge sample size, my estimator should be really close to the thing it's estimating, right? If I have an n of 100,000 or something, it doesn't matter really at all whether I estimate sigma with S or whether I actually know sigma. I have such a huge sample size, I pretty much know sigma either way. So really this comes into play that we don't, this issue that we don't know sigma when we have smaller sample sizes. And that was really what this guy Gossett was looking into, is with small sample sizes, which is what he was dealing with. How do we get something similar to this kind of idea up here, or this kind of central limit theorem? And he discovered this distribution and this mathematics and he published it, but because he was working for a private company, obviously they would have liked to maintain the upper hand over their competitors. So they wouldn't have wanted him to publish this. So he published it under a pseudonym. And the pseudonym he chose was Student. I don't know why he chose Student, but It was published under, the name student. And so that's why it's the student's t distribution. He chose to use the letter t instead of z to represent this kind of similar quantity with the sample standard deviation in the denominator. So that's kind of the background of how this got out there and why it has this kind of funny sounding name, the student's t distribution. It's because it's the t distribution belonging to the person named student, who is really this guy Gossett. And then, of course, at some point it came out that he was the one who was actually behind the publication of it and all that. And probably like after he was retired and couldn't get in trouble or something. I don't know all the details, but fun little backstory. So what do we know about t? Well, we know a couple of different things. The PDF is given by this function. Here, c is just some constant. It's this kind of crazy looking constant. But basically, what the t distribution looks like, and we can think of this as kind of like a standard t distribution. This is like the equivalent for the standard normal. But this kind of standard t distribution has two things. Number one, it kind of looks like 1 plus x squared to a negative power. It looks like 1 over 1 plus x squared-ish. But it's raised to some power. That power is often written with the Greek letter nu. So this thing that looks like a kind of curly V is the Greek letter nu. It's the Greek letter n. So this looks more or less like 1 over 1 plus x squared to the nu power. And that's this power up here. I mean, it's a little closer to nu over 2, but more or less it looks like this kind of a shape. 1 over 1 plus x squared, actually, if you graph it on your calculator, it looks pretty much like a normal distribution. It follows that same bell-shaped curve pattern. But we have this exponent nu up here. So we have a family of t distributions, even a family of standard t distributions. The same way that maybe for general normals, we could pick mu and sigma however we want, or well, mu is any real and sigma is any positive real. And that would give us a different normal distribution. But when we go to standard normal, that's just like its distribution. That it is what it is. For t, we have, even for the kind of standard t distribution, so to speak, we have a parameter that we can choose, this nu. We think of nu being a positive integer. And the really important thing to note about the t distribution is that 1 over 1 plus x squared, while it has that same bell-shaped distribution, if we were to look at, say, a normal distribution, maybe it looks like this. So maybe this is z. The normal distribution looks more or less like e to the negative z squared. This thing goes to 0 very, very fast as z goes away from 0. A t distribution has heavy tails. It still has the same general shape, but the tails are much thicker and the middle is depressed a little bit. And it's important to note that the tails aren't thicker like a normal distribution with just a higher standard deviation. They're like fundamentally thicker. Like as we go farther out into infinity, no matter how big you would make the standard deviation in a normal, the t is always going to end up with heavier tails. So this might be like a t distribution with, say, I don't know, maybe nu equals like 3 or something like that. It still has this kind of bell-shaped characteristic, peaked in the middle, tailing off to the side, symmetric about its mean, 0 in this case. What happens if we increase nu? What happens if we have a nu of like 10 or 15? It's still a heavy tail distribution, but it starts to look a little more like the normal. So this black curve might be something like t with maybe nu equals 15. What happens if we have a nu that's very large? So something like maybe 30 or 50, something like that. It starts to look a heck of a lot like the normal distribution. It's going to be a little bit shorter in the middle here. I'm trying to draw that, but I'm ending up more or less on top of the line. And then it's going to be a little bit thicker in the tails, but just by a hair. So this red curve might be like the t distribution with nu equals, say, 50 or something like that. Basically looks like the standard normal. So we can say as nu goes to infinity, t goes to z. The t distribution looks more and more and more like the standard normal. This is something that can be proven carefully, but it's also something that we can just observe by going to a calculator or graphing program and plotting the t distribution with different increasing values of nu over top of standard normal. Okay, so this does kind of make sense, right? If I have a large, and I forgot to mention this next part, this this parameter nu, the Greek letter n, we often call it the degrees of freedom, and often, particularly in this case, we take nu to be n minus 1. It's the sample size of our data set minus 1. Remember, we know n up here from our data. So roughly speaking, nu is like sample size. And as nu gets larger, my t distribution looks more and more like a standard normal. And that makes sense because as my sample size gets larger, the difference between knowing sigma and having to estimate sigma by s gets smaller and smaller. My estimate gets better and better, again, by that assumption of it being a good estimator. That convergence property was one of our criteria for being a good estimator. And we're kind of pretending that S is a good estimator of sigma. Even though that's not quite true, we're saying it's good enough for our purposes. So for large n, for large sample size, the difference between these two situations is minimal. And using this t distribution instead of z for large n or for large nu is also minimal. They basically look the same. Where we really see the difference is when we have small n, when there's a big difference between knowing sigma versus having to estimate sigma on the basis of a pretty small sample where there's still a lot of uncertainty about what mu is, but also what sigma is. We want to account for that additional uncertainty, which is significant. That's when we see our t distribution looks a lot different than our standard normal. That's when we really have to be cautious, these small sample situations, about using the correct distribution. In fact, some stats textbooks will just say anytime that n is bigger than 30, whether or not we know sigma, just use this formula. I personally don't like that. I don't, because n bigger than 30 is a rule of thumb. I mean, we're using it to use the conclusion of the central limit theorem here, but I think it pushes it maybe a step too far to say, just pretend we know sigma whenever n's bigger than 30, because at that point, why wouldn't we also just say pretend we know mu and just say that mu equals x bar observed at that point? I don't know. So I take a little bit of umbrage with that approach, but some well-regarded stats textbooks by very reasonable authors will take that approach that will just say for large n, just use this whether or not you know sigma. We're not taking that approach, but just making the point that for large n, for large sample size, the difference between the two is small, really where we see a substantial difference between the two approaches is for smaller sample size. And it turns out that, again, with this statement up here, that this t-distribution is what we get when we take our standardized version of the random variable x bar, but where we're using the sample standard deviation instead of the known population standard deviation, we get this t-distribution, and our confidence interval, get a little more room here, our confidence interval really looks exactly the same as up above. We have our point estimate, x bar observed, plus or minus a margin of error. Our margin of error is a statistical distributions index times standard error times standard deviation over root n, or we're now just using S, the sample standard deviation, instead of sigma, the population standard deviation. So what's the real difference here? The real difference is what distribution do we use to generate our index number? We're not using Z, we're not using the standard normal table like we did up here. We're not using Z alpha over 2, the Z index with alpha over 2 area to the right. We're using the T index. We're looking for, say, on a given, maybe this T distribution with nu equals 15, we're looking for the T index with alpha over 2 area to the right, instead of a Z index with alpha over 2 area to the right. We can see that for a given alpha, if I say how far out in the tail do I have to go for this T distribution, this green one, to get area alpha over 2 to the right, versus for my Z index, how far out do I have to go to get alpha over 2 area to the right? Z alpha over 2 is closer to 0 than T alpha over 2, right? Because the Z distribution goes to 0 faster, which means as I start out here to the right of my tail and work my way to the left and start accumulating area until I get alpha over 2, I've got to work my way closer to 0 because I'm not accumulating much area at all in that tail, versus the T distribution that is accumulating a decent bit of area in that tail. So I note that Z alpha over 2 is less than T alpha over 2. So switching from a Z interval to a T interval makes my margin of error bigger. My margin of error is bigger to account for the extra variability that's added into the system by estimating sigma by S as well as mu by X bar. Okay, so let's look at how to find some T numbers, and then we'll look at a couple examples of actually computing confidence intervals. So let's find T 0.05 with 10 degrees of freedom. Give me 1 second here. Oh, I just saw somebody send in chat, good morning, good evening, and good night. Yeah. Yeah, was it good morning, good afternoon, good evening, and if I don't see you, or no, good morning, and if I don't see you, good afternoon, good evening, and good night. That was what it was from the Truman Show. Sorry, I just saw that in chat. I had my window hidden. Okay, so how do we find such a T number? Well, if we go to the PDF tables that I put in chat or that are on Blackboard, let me actually pop it in chat again, just in case anybody joined a little bit late. So the t-table is in chat again. So if you download that and open it up, and let me switch my share here. Sorry about that. If I switch my share here, I see I have a t-distribution chart. But I note that it actually looks substantially different than my normal distribution chart. So we have to keep in mind that a couple of things. Number one, we're usually not looking for areas for certain t indices like we were with normal distribution, where we want to say, what's the area to the left of like z equals -1 or something. That was a z distribution question that we were interested in answering in chapter 6. So we needed a table like this where I could really finely really refine my z index and then find an area. In this case, I only need t indices corresponding to certain areas. And also, I kind of mentioned this before, that I guess in theory, we could come up with a confidence interval that's like a 92.5% confidence interval or an 89.125% confidence interval. But like in practice, nobody does that. We're basically always finding 90, 95, or 99% confidence intervals, or numbers very closely related to those three confidence levels. So nobody really tries to find a 92.75% confidence interval. That's just not something that people are interested in doing, typically. That's not to say it can't be done, but you might use Excel or something if you wanted to do something a bit offbeat like that. So first off, the kind of questions we're trying to answer here are different. We're looking for a particular list of alphas, maybe 6, 8, 10 different alphas. We want to find t indices. The other thing that we note is that the degrees of freedom, or this parameter nu, means that we have lots of different t distributions. Where we only had one standard normal, we have lots of, you might call them like standard t distributions. So if I wanted to give you a t-table that looked like this, I would have to give you like 50 pages, like 50 t-tables or something. One for nu equals 1, one for nu equals 2, one, right? For all these different values of the degrees of freedom parameter. But this is way overkill for what we need to do for these kind of problems. Just finding a t-index for a few different probabilities, right? We have a ton of different probabilities in here. We have a couple hundred, I think, in here. But we only really need like 8 or 10 of them. So the t-table leverages that. The t-table looks at this the opposite direction. It says, okay, which t distribution am I on? Am I on the one with 1 degree of freedom, with 2, with 5 degrees of freedom? So this index column on the left side here indexes which t distribution I'm on, which degrees of freedom I'm working with. And then the right tail area is what's given up here. We have one line for one tail area and another line for a two tail area. So if I'm looking for a 95% confidence interval, I know my two tail area is 5%, which means 2.5% in each tail. So one tail area of 2.5%, two tail area of 5% that's combined between the two tails. So if I'm looking for t subscript 0.05, or one tail area of 5% with degrees of freedom 10, I'm looking for a one tail area of 5% with degrees of freedom 10. So I'm looking to be in this row with a one tail area of 5%, which means in this column, then my t value, my t index is 1.812. Or in other words, probability that t is bigger than 1.812 is about 0.05 when nu equals 10. This is my t index that I would use maybe in a confidence interval where alpha over 2 was 0.05, or where alpha was 10%, or say a 90% confidence interval with 10 degrees of freedom, or with maybe a sample size of 11. So what if I had, say, a sample size of 25, and I wanted a 95% confidence interval? And I want to find the t index corresponding to this setup here. Well, I know my degrees of freedom is n minus 1, or 25 minus 1, or 24. My 95% confidence interval tells me that I have a two-tail alpha of 5%, or a one-tail alpha of 2.5%. So what is my t 0.025? What is my t index that I would use for this confidence interval? Well, again, I would look for degrees of freedom 24. And then remember, one tail area of 2.5%, two tail area of 5%. That's my middle column here that's bolded. Right, 95% confidence interval is a pretty common one. So it's right in the middle, it gets bolded. And I see my t index is 2.064. So this is how we look up t indices on our t-table. Now, two notes that I want to point out. The first is, if I go down my degrees of freedom list here, it goes by every digit increment until I get up to 40. Then it jumps by 5, and then 10, and then by 100. So what do I do if I had, like, 57 degrees of freedom? That's between these two. I just pick the nearest one, I suppose. I just round 57 to 60, and then find whichever number I need. It's not that big of a deal, because we can see that the differences are like 0.01-ish from one line to the next, especially once we get up to a large number of degrees of freedom. Down here, they're more significant, right? This is like 0.2-ish. But once we get up to larger degrees of freedom, the difference from one line to the next is like 0.01 or so. That change in like the third significant digit is probably not going to, a small change in the third significant digit is probably not going to really throw off our calculations much at all. So making an approximation for the degrees of freedom for a larger number, not a really big problem. The other thing we notice is the very last line down here, the quote large degrees of freedom, or some tables will say infinity there. We might actually recognize these numbers from our previous work: 1.96, 1.645. This reminds me of standard normal numbers, right? We've seen these numbers 1.96 and 1.645 come up quite a bit. 1.28, 2.33, I don't remember if we saw that or not, or 2.58. But we've definitely seen these two several times. In fact, this last line, remember that the t-distribution, as the sample size or as the degrees of freedom goes to infinity, approaches the standard normal. So this last line in this table is actually just the standard normal values. So some tables will even just say z here instead of large. This is the standard normal. These are the standard normal indices. So when you're working with confidence intervals, if you need a z-score, if you need a z-index for a confidence interval, a lot of times it's actually quicker to come to the t-table, look up whatever tail area you need, and then just jump all the way to the bottom and grab your z number off of the t-table. So it's a little bit of a shortcut. You can still do it with the standard normal table, nothing wrong with that. So if you don't, if you forget why that's true or forget about it or something, you can still find your numbers here or use the field of the table and then work your way out to find the indices. That's still perfectly valid. But if you want a shortcut for finding the z indices for these confidence intervals where we're at these specific areas that are pretty common, just look up your area, go all the way to the bottom of the t-table to find your z numbers, because z is the limit of the t-distribution as degrees of freedom go to infinity. Okay, let's look at an example. So suppose that suppose the body temperatures are normally distributed. A sample of size 10 yields a sample mean of 98.25 and, importantly, a sample standard deviation of 0.73, both degrees Fahrenheit. Construct a 95% confidence interval for the true mean body temperature. And then based on this confidence interval, does it seem feasible that the true mean could be 98.6 degrees, which is, I think, kind of the famous number that everybody says that the mean body temperature should be. I mean, our sample mean is a bit different than 98.6, but really what we're trying to address here is, once we account for sampling error, the fact that our sample of size 10 might have just happened to have gotten a few folks who have a slightly lower body temperature, either that day or in general, and a few fewer folks who have a higher temperature. Do I think this 98.25 being lower than 98.6 could very well just be due to a sampling error like that? Or do I think that that's so unlikely that I think that the true mean body temperature is actually different from 98.6? Again, this is kind of dipping a toe into chapter 8 with hypothesis testing, where, kind of stretching the limits of what the confidence interval is really comfortable saying in and of itself, but we're just showing some of what we can do with the confidence interval. Okay, so what do I know? I know my sample is size 10, sample mean x bar observed 98.25, sample standard deviation S is 0.73. I know my confidence level is 95%. And I don't know mu, of course, because I'm looking for a confidence interval for the mean. But I also don't know sigma, right? I don't know the population standard deviation. Let me copy my formula down here. Oh. Okay, so I know n. I know the sample standard deviation. I know x bar observed. Most of this is just a plug and chug. Most of this is just a pretty simple calculation after I find my t number. So I need to find t alpha over 2, or I need to find t 0.025. 95% confident means my error rate, my alpha is 5%. 1/2 of that is 0.025. So I have a one tail area of 0.025 or a two tail area of 0.05. I also need to know my degrees of freedom, which remember is just n minus 1, or 10 minus 1, or 9. It's kind of an aside. Why is degrees of freedom n minus 1? That seems like kind of a strange thing. It's also kind of related to that n minus 1 that we saw pop up in the sample variance versus the population variance. And basically, the name gives us a clue, the degrees of freedom. If I have a sample of size n, kind of at the outset, I can choose all of these n numbers any way that I want, and that would be a valid sample. But then if I have one constraint, specifically that I know that X bar observed has to be 98.25, that constrains what numbers I can choose. In other words, I can choose 9 of those numbers, 9 of those 10 numbers any way I want, as long as you leave me one number left over that I can pick any way that I want, then I can force X bar observed to be 98.25. So I have starting off with n degrees of freedom because I have a sample of size n. I have n numbers that can be chosen any way that we want. But then I have one constraint, so that removes 1 degree of freedom. You need to leave one number left over at the end. You can pick the other n minus 1 any way you want. You have to leave one left over to kind of take up the slack and force X bar observed to be what we actually observed it to be. So that's just a little insight into why it's called degrees of freedom and why it's n minus 1. But here we have 9 degrees of freedom. So I need to find the t-index with a one tail alpha of 0.025, a two tail alpha of 0.05, and 9 degrees of freedom. One tail 0.025, two tails 0.05, that's this column. I usually like to check both ways because you see that sometimes there's like a 0.01 in both rows, or there might be a 0.05 in both rows, right? So sometimes it can be easy to grab the wrong one, but if you remember 0.025 in one tail, 0.05 in two tails, this is the column that has both of those numbers. And then I have 9 degrees of freedom. So that gives me a t-index of 2.262. And now I have everything that I need for my formula. So maybe I'll start by computing the margin of error. My t-index times my standard deviation 0.73 over root n over root 10. Note that the root n is root 10. It's not an n minus 1 there as well. This is still just a regular old n. And I can come over to my calculator. Well, I missed the decimal point there. And I get about 0.522. As an aside, this margin of error is in units of the original data, because this 0.73 is the only number in here that has a unit associated with it, and it's a standard deviation, units of original data. And then my lower and upper bounds for my confidence interval are going to be X bar observed, 98.25 minus or plus 0.522. So there's my upper bound, and if I do second enter, I can change the plus to a minus, and there's my lower bound. So my 95% confidence interval for mu, the true mean body temperature, is 97.73 up to 98.77. And remember, if I want to be technically correct, how I would interpret this is that there's a 95% chance that an interval constructed in this manner would cover mu. So there's a 95% chance that this interval covers the true mean mu. Does it seem feasible that the true mean could be 98.6? I do notice that 98.6 is within this interval that I found. It's just a little to the left of the right endpoint. Yeah, so it does seem feasible that the true mean could be 98.6 degrees, and that the reason we got an X bar observed of 98.25, less than 98.6, could very well be due just to sampling error, just to the fact that we took this sample of size 10, and if we got a different sample of size 10, maybe we would have gotten an X bar observed much closer to 98.6. So this isn't so far away, 98.25, that we would consider it unlikely for true mean body temperature to be 98.6. Again, that's touching a little bit into the chapter 8 hypothesis testing material, but showing you kind of what inferences we can make from confidence intervals. Okay, any questions so far? So let's look at an example of a one-sided confidence interval. We could construct one-sided confidence intervals for mu when sigma is known, for p, for mu when sigma is unknown. So this isn't just specifically for this section, but we're covering it in this section just because at this point we're a little bit used to confidence intervals. Our goal here is to find the 95% one-sided confidence interval minus infinity to u for mu, the true population median claim amount. In other words, I want to find something like an upper bound for mu. So how does this change things? Well, here, if I think of my t distribution, my interval goes from minus infinity up to u. So it's kind of the whole area to the left. This area is 95% to the left, leaving me with 5% to the right. So how does having a one-sided confidence interval change things? Well, the most substantial change is that we put all of our error rate into one tail. So here I'm finding T alpha, or T 0.05, not T alpha over 2. That's really the most substantive change. And then, of course, the other change is that we don't find a lower bound, we just find an upper bound. The upper bound being our point estimate plus the margin of error. We put all of our error into the right-hand tail, and then we only find our one bound, our upper bound, X bar observed plus the margin of error. We don't find the lower bound. We could also find a one-sided confidence interval the other way. We could ask for a lower bound instead, and then everything would just be symmetric. Okay, so what do I know? I know my sample information. Sample size of 31, X bar observed of $1,000, sample standard deviation of $3,000, and I want a 95% one-sided confidence interval. So my one tail alpha is 5%, and my degrees of freedom are 31 minus 1, or 30. Let me go over to my t table. 30 degrees of freedom. So coming down here to this row, And I have to be careful here. One tail area, make sure I get the right one, of 5%. So second column from the right, not the true tail area 5%, but one tail area 5%, second column from the right, and 30 degrees of freedom gives me a T index of 1.697. Or my upper bound is going to be, my right side of this confidence interval is going to be X bar observed, 1000, plus 1.697 standard errors, or 1.697 times S, 3000, over root N, root 31. Again, under the root, I still use N 31, not N minus 1. So I need 1000 plus 1.697 times 3000 over square root of 31. And that looks good. So this gives me 1914 or so. And I can say that the the 95% one-sided confidence interval for mu, got an extra comma there, is minus infinity to 1914. Or I can say something like I'm 95% sure that the number 1914 is greater than mu. So 95% certain that 1914 is greater than mu. Remember, this upper bound of this confidence interval was what's random, because on repeated samplings, I would get a different X bar observed and probably also a different S. So U is what's random, mu is fixed. From the perspective of the frequentists, anyway. So again, what's the difference between the confidence interval from mu when sigma is known versus unknown? Really, it just comes down to what distribution we use to look up our index. Do we use the Z distribution? Or do we use the T distribution? And if we use the T distribution, we have to just remember degrees of freedom is N minus 1. And the setup of the table is just a little bit different than Z. The setup of the table is kind of backwards, because fundamentally we're doing an inverse problem every time that we use T, at least in this context or in hypothesis testing in chapter 8. Any questions so far? Okay. All right, so let's look at the next topic, confidence intervals for variance and standard deviation. This is the last topic, last main topic we'll cover in confidence intervals. But we'll also cover kind of a side topic that's a more empirical, more data-driven topic called bootstrapping. But this is the last of the formula-based confidence intervals that we're going to cover. So recall that S squared is a good estimator of sigma squared. We talked about what it meant to be a good estimator a class or two ago. And for our purposes, we're going to consider that S is a good enough estimator of sigma. That's kind of our rule of thumb. We're going to treat S as a good estimator of sigma. If we think back, we knew that X bar was a random variable. And we knew that if we took that random variable and transformed it by subtracting the mean and dividing by sigma over root n, we got a distribution that was standard normal. That was what our central limit theorem said. So X bar is our estimate of mu. So when I was interested in estimating mu, I was interested in what the distribution of X bar looks like. Now I'm interested in estimating variance or standard deviation. I'm interested in estimating, say, sigma squared by S squared. Is there a way that I can transform the distribution, transform the random variable S squared to come up with a distribution that I know what it is? And the answer is yes. If I consider the transformation n minus 1 times S squared over sigma squared, it turns out that, again, folks who are a lot smarter than me have worked out that this is the type of distribution that is called a chi-squared distribution. So this thing, it looks a little bit like an X, especially in this font, but if we have like A, B, C like this, the Greek letter chi looks like this. It's kind of an X with like a long right-hand tail that swoops down below the whatever this bottom line is that all the letters sit on. So it's kind of like a P or a Q in that sense. It looks like that. This is the Greek letter chi. And I try to make my chi's look extra curly and my x's look more straight. But if you're ever not sure which one I'm writing, just ask and I'm happy to clarify. So this is the Greek letter that's kind of like CH, kind of makes a sound something like Locke or Bach or whatever. So that's chi. So chi-squared distribution. Very important, the name of the distribution is chi-squared. So similar to how we have like the Z distribution or the T distribution, we have the chi-squared distribution. So when you see that superscript 2 on this chi-squared, that's part of the name of the distribution. It doesn't mean, whatever number you get from a table, also square it. It's kind of, in a sense, already squared as part of the calculation of the distribution. And where does this distribution come from? If we consider a standard normal, Z, and actually if we consider several standard normals. So if I thought of like rolling one die, it has a certain probability distribution. If I thought of rolling 10 dice, that would have like 10 copies of that same probability distribution, right? Or if I have a standard normally distributed random variable, and I just like took 10 draws from that random variable, I could get several draws from that standard normal random variable. These would be independent. Knowing what draw I got on the first draw doesn't tell me anything about the 5th or the 8th draw. And these would be identically distributed, all coming from a standard normal. If I construct a new variable based on all of these draws from a standard normal, I could construct this new variable in a number of different ways. I could say average them together or something, or I could choose to take each number that I drew, first square it, and then add together those squares. If I do this, if I start with n standard normal distribution numbers, n numbers coming from a standard normal, square each of those numbers, then add them together, that's how I get a chi-square distribution. What should the chi-square distribution look like? Well, I know that normals can be any real number, standard normals, but normal squared, they're only positive numbers. I guess it could be 0, but that's with probability 0. And then if I add up a bunch of positive numbers, I get a positive number, right? Most of the time, my standard normals, they end up close to 0. So if I square them, they stay close to 0. And then I add them up, and the sum of a bunch of things close to 0 isn't all that big. But occasionally, even with a standard normal, I might get a z-score of 3 or even 4, and I square that, and that turns out to be a really big number, 9 or 16 or something. So occasionally I get kind of a somewhat large number, but then I square it and it becomes a really large number. So most of the time, and of course, if I add a really large number to a whole bunch of moderately sized numbers, that's a really large number for the sum. So most of the time, my sum of these squared normals is going to be kind of a small or moderate number, but sometimes it's going to be a very big number. This is going to be a distribution that is skewed right and only positive. I would expect it to still have a bit of that standard normal shape. But this is what my typical chi-squared distribution looks like. It has a little bit of this kind of peaked shape. It's maybe a little bit symmetric, but it does not go to the left of 0 because we constructed it by adding together a bunch of squares of things. And also the larger n gets, this peak, this hump moves to the right. And actually for pretty large n's, I can have something that looks a heck of a lot like a normal distribution. Once that peak moves far enough away from 0, here's 0. Once it moves far enough away from 0, it starts to look pretty symmetric, peaked in the middle, tailing off to the side. So for large n, this starts to look kind of normal. But for smaller n, the skewedness is pretty obvious. Now, I would like to use this as the basis of a confidence interval, but I have a little bit of a problem here. The z distribution, the t distribution, these are both symmetric about 0. So when I wanted to create a symmetric confidence interval, I just took kind of a plus or minus margin of error approach, right? If this was t, or if this was whatever, t alpha over 2 here, forget about these ones, this would be negative t alpha over 2 by the symmetry. If I want some semblance of symmetry in the chi-squared distribution, I've lost that symmetry about that that central point, that mode, or the most frequently occurring value, or the peak. How do I impose symmetry in this kind of sense? Well, what I would do to impose symmetry I would choose a chi-squared lower bound and a chi-squared upper, or maybe I'll call it chi-squared left and chi-squared right, so that we're being very clear about which one is left and which one is right, and we'll see why that'll be helpful in a minute here. And instead of symmetry, where I'd have something like chi-squared left equals negative chi-squared right, that's kind of the symmetry that I had before, I've lost a little bit of that symmetry in the indices. But I could impose the symmetry by putting alpha over 2 area in each of these tails. Here, chi-squared left and chi-squared right are both going to be positive numbers. Chi-squared right is going to be a larger positive number. The symmetry comes from the areas and the tails being equal. And yeah, so the area and the tails is equal. This gives me whatever confidence value in the middle here, say 95% confidence level, that's the area in the middle, and then 5% combined between the two tails. So I noticed that one of these areas is a left-hand area, one of these is a right-hand area. We're going to have to make an adjustment to use our table. And there's one more thing I wanted to mention. Oh yeah, the other very important thing is for a given chi-square distribution, we're adding together n standard normals. Well, pretty clearly, the more standard normals we add together, the more positive terms that I have here, the larger this number is going to tend to be. Chi-squared also has degrees of freedom. Different sample sizes yield different degrees of freedom and different chi-square distributions. So our chi-square table, if I bring it up here, let me actually pop it in chat first. It usually doesn't let me share in chat if the file is open. So I'll pop it in there first and then bring it up for you. So my chi-square table, I see these are areas to the right of the critical value. I have my areas across the top, degrees of freedom on the left. This chi-square table is set up the same as the T table, where we're given indices in the middle, right tail areas across the top, and then degrees of freedom indicating the different distributions going down the left. So similar setup to the T table for the chi-squared. Again, because the questions that we're asking about from the chi-square distribution are questions about critical values. We're not looking for the probability that, you know, the chi-squared is less than some number. We're looking for these indices. Okay. Okay, so what do I have then? I see that n minus 1 s squared over sigma squared is a chi-square distribution. And if my interval looks like a chi-squared being between this number chi-squared left and this other number chi-squared right, well, that's n minus 1 s squared over sigma squared being between these two numbers. Right, this n minus 1 s squared over sigma squared is just the thing up here that we said is the transformation of s squared, our estimator, our random variable, that looks like a chi-squared. We have to make this transformation to make things work out nicely, the same way we had to make this transformation to x bar to make things come out to be a standard normal. Well, what could I do? I suppose I could invert everything. If I invert everything, flipping the numerators and denominators, that switches the inequality signs. And then I could multiply through by n minus 1 s squared. That's what I have here. Notice that chi-squared left is associated with the upper bound and chi-squared right with the lower bound. But other than the different chi-squared numbers, the two upper and lower bounds look pretty much the same. Why is chi-squared left associated with the upper bound and chi-squared right with the lower bound? Well, chi-squared left is the smaller number. If I put the smaller number in the denominator, that makes the whole fraction bigger. Chi-squared right is the bigger number. If I put the bigger number in the denominator, it makes the whole fraction smaller. So that's the upper and lower bounds, upper and lower bound formulas for our confidence interval for the variance. And here, just like in the t distribution, we take degrees of freedom to be n minus 1. This gives me the confidence interval for sigma squared. To get a confidence interval for sigma, again, it's a little messy, so this is kind of a rule of thumb kind of idea here, but we're just going to square root everything. We'll just square root up our upper and lower bounds to get upper and lower bounds for sigma. Okay, so let's look at an example. So suppose we're interested in knowing the variance of standard deviation of the masses of dollar coins. A sample of size 20 yields a sample standard deviation S of 0.04111 grams. Note that we don't have X bar observed because we actually don't need it, right? X bar doesn't come up anywhere in here. So interestingly, S or sigma does come up in the confidence interval for mu, but X bar does not come up in the confidence interval for the variance or standard deviation. So we actually don't need X bar observed. And we want the 99% confidence interval. So I see my formula. I see my formulas both look pretty similar. And n minus 1 s squared over a chi-squared number. And chi-squared left is the smaller number. It's in the bottom. It's going to be associated with the upper bound. And chi-squared right is the larger number. The larger number in the denominator is going to make the whole fraction smaller. It'll be associated with the lower bound. Or this is going to be 19 times s squared over a chi-squared number. And just like before, once we have the formulas, it's a pretty straightforward process after we find our indices. So if I draw myself a little picture here, this is chi squared with 19 degrees of freedom. I want a 99% confidence level. So I know that there's 99% in between these two chi-squared numbers, total of 1% combined between the tails, or 0.5%, 0.005 in each tail. Now, if I look at my chi-square table, the areas that it gives me up top are areas to the right. So for chi-squared right, I need an area to the right of 0.005. That one's ready to go. For chi-squared left, well, I have an area to the left of 0.005, so I've just got to flip that and make an area to the right of 0.995. And then again, degrees of freedom, 19. So area to the right of 0.995 for 19 degrees of freedom gives me a chi-squared index of 6.844. And remember, this equals chi-squared left. I don't take 6.844 and then square it. This is just what the number is. And then the area to the right of 0.005, also for 19 degrees of freedom. I see this was the leftmost column. So this is kind of like a mirror symmetry here in this table. So 0.005 gives me the rightmost column on the degrees of freedom 19 line, and that's 38.582. My bigger number goes in the denominator of the left or the lower bound. And my smaller chi-squared number goes in the denominator of the upper bound. It's not the end of the world if you get them backwards. You'll pretty quickly see that if you get them backwards, your upper bound is the smaller result and your lower bound is the larger result, and then just flip them. So not a big deal if you're paying attention and you get them backwards. Just make sure that everything, all the inequalities line up properly at the end. But I'm looking at 19 times 0.04111 squared divided by 6.844. And for my upper bound, that is 0.0047. And I might be a little concerned here. I might be tempted to compare this with that number and say, wait, this is supposed to be an upper bound, but it's below my point estimate. But remember, this is for sigma squared. So this is in units of square grams. What the heck does that mean? So my confidence interval for sigma, for the upper and lower bounds, I'll square root that answer. And this gives me 0.068 or so. So I don't want to compare these numbers, but 0.068 I do note is above 0.04. That looks good. What about my lower bound? If I do second enter, that brings up the previous thing I typed in. If I hit second enter again, that brings up the next previous. So this bit that I typed in. And I just need to change my chi-squared number. 19 times 0.04111 squared, that's all the same. I need 38.582. And this gives me 8.3 times 10 to the minus 4. Again, I don't want to compare this to that number up there. I'm probably interested in a confidence interval for the standard deviation because that has the same units as everything else. So I go ahead and square that answer that I got, and I get 0.029 or so. Or my 99% confidence interval for sigma is 0.029 to 0.068. Now, one thing to notice about the upper and lower bounds is these are not symmetric about my point estimate, 0.04111. So this 0.0288 number is 0.04111 minus what? If I subtract 0.04111 off of it and then change the sign, I see this is about 0.012. So the kind of margin of error for the lower bound is 0.012. For the upper bound, wrong screen there. For the upper bound, 0.068 minus 0.04111 gives me 0.027 or so. So from my point estimate, I went about 12 units to the left and about 27 units to the right. This distance is about 2 times that distance. In some sense, this kind of makes sense, right? If I'm looking to analyze variance of their standard deviations, these have to be positive numbers by construction. I mean, that kind of meshes with my chi-squared not having anything in the negative side, so that kind of makes sense. And the positive numbers on the right side, I see that this is skewed right. I know that variances of standard deviations are disproportionately affected by outliers, and they're disproportionately affected to the right by outliers. So if there's a bit of an outlier in one of these, then that's going to disproportionately pull the variance or standard deviation to the right. So it does feel in some amorphous sense like my confidence interval, like it's sensible for it to be a little skewed, maybe in a more rough sense than the technical sense, to the right. Then maybe we have more allowance for variation on the right than on the left. Maybe that kind of feels right. Are there any questions on anything so far? I don't think we have time to get this last one in the last 8 minutes or so, so we'll save that for next time, wrap up this section next time. But any questions on anything from today or from confidence interval so far? All right, then we'll end a few minutes early today. We'll wrap up the last problem in this section next time. I haven't decided whether I'll cover bootstrapping in class or post it as a supplement. I'll take a look at the course schedule and our classes that we have coming up as we get near the end of the semester. I try to slot things in so that we can cover all of the material we need to. We do have a couple optional topics, and bootstrapping is kind of an optional topic. So I'll look at our course schedule and decide whether we're going to cover bootstrapping next week or next Monday, or start into hypothesis testing. But I would strongly recommend that that you pre-read hypothesis testing before next week. Just glance through the first section or two of chapter 8, and then that'll give you kind of an idea of what we're doing in hypothesis testing. It's not so much the math that's new and complex. It's really the logic and the goals of hypothesis testing that make it somewhat complex. So pre-reading before that gives you a little bit of an idea of what to expect, and I think makes it a little easier to interpret when you see it the second time around rather than for the first time. So definitely pre-read a section or so in chapter 8 for next week. Otherwise, I will see you next week. Have a good weekend.